Bonjour tout le monde. Mon nom est Octave Cornéa et je suis le directeur du Centre de recherche mathématiques. So I'm going to continue in English. In English also, my name is Octave Cornéa, and I'm still the director of the Centre de recherche mathématiques. So the center was founded in 1968, and already in 1970, it initiated the Chaire Aisenstadt lectures. There are generally three lectures given by one speaker. And one of the lectures is supposed to be for a general mathematical audience. And the lectures bear the name of a generous donor who was a successful businessman and a mathematics enthusiast. And this building also, of course, you know, carries his name. And the thematic semester system was launched in the early 70s by the CRM and also sort of the same time by the MSRI. And these lectures became an important component of these thematic semesters. Oh, too many directors on the screen. Okay, along the years, many distinguished mathematicians have held these chairs. And generally now there are two speakers associated to each of the year's two thematic semesters. So we have roughly 4 speakers each year. And today we have the pleasure to receive Professor Rachel Kuske, who is at Georgia Tech, and my colleague and maybe old friend Konstantin will say, no, not old friend. You're a friend for a long time, but you're still a very young friend. Also old. In any case, I pass it to you to introduce Rachel.
It is a great pleasure to have Rachel here. She's currently a professor at Georgia Tech. She was chair there for 5 years. Before that, you were chair at UBC. She's got a lot of distinctions. I'm not going to say all of them. I did write a few of them down. I put my glasses on to read them.
I don't need to read them.
Yes. She's a SIAM fellow. She had a Canadian research chair at UBC. She was a Simons fellow at the Newton Institute. She got the Krieger Nelson Award from the Canadian Math Society. She got the Math Service Award from the Association of Women. And there are a few more. But her area of expertise, which is why we're very happy to have her here this semester with us, is in applied nonlinear dynamics from a stochastic multi-scale perspective. And so I guess we're going to learn today about whether the Earth is round or a square, a cube.
Thank you. Yeah, I think they're still connecting me. Okay, looks like we're back in business. Great. So thank you very much for the invitation. It's a great honor to be here. Also nice to be back in Canada. And also it's been really fun so far being part of the computational dynamics thematic program. I'm connected in various ways, but not central, I think, in any one area. So I'm actually learning a lot, which is fantastic. Okay, so today I'm going to talk about, is the world smooth or non-smooth? This is not a talk about the Flat Earth Society. I'm not even sure if I'm going to answer that question, but we're going to see what math has to tell you about that. And in terms of this question, is the world smooth or non-smooth? Spoiler alert, I'm going to say the answer is yes. So let's see what that looks like. Okay, so to kind of put things in context, let's first think about what it means to be smooth, right? So I'm going to show equations, although, again, I'm taking the interpretation of general audience to sort of mean not much math background. But so most of everything you need to know here is just going to be shown with the pictures. So you don't really have to look at the equations if you don't want to. One of the simplest examples is what we might show our calculus students where we just teach them about rates of change. This is a simple heat transfer model that just says, okay, if we just have, without any external heat source or anything like that, if we just have an ambient temperature, for example, if it's cold outside, we don't heat the building, over time, the temperature of the building is going to go to whatever the temperature is outside. So that's basically just saying the rate of change here, this dT dt, is just going to be proportional to the difference between what our temperature is and the ambient temperature. So that means if we're above the temperature, we follow the blue line where things decrease. If we're below the ambient temperature, we're going to increase to go up to that temperature. Okay, but we notice here these two curves are what I would call smooth. That is, they just gradually vary, and we just gradually reach the ambient temperature. Okay, so that's kind of a standard thing we would go through in our simple calculus class. But of course, we express this kind of evolution, could be in time, could be in space, in many, many different applications, as I've mentioned here, from physics to disease to finance to whatever you want to choose. Now, that doesn't mean that everything looks nice and gradual changes, right? So, for example, here I have what happens if we have a traffic density model, right, where you might have some larger density, at some point in space of your traffic, and away from that lower density in traffic. If you let that evolve, the typical equation you would have, we might eventually get a traffic jam. And there you would see this abrupt change from low to high density in the traffic. So many equations can evolve to that kind of what I would call non-smooth or sharp change. But there's many problems where we actually bake the non-smoothness in. And by that, there can be many ways, as we'll see, to do that. But a common way that we bake in non-smoothness is we think in terms of control, or we turn something off and on like a tap, or here I mentioned, trading. We change our portfolio by making a trade, and that's quick, right? So I'm going to talk about what happens if we kind of give up the nice mathematics where everything gradually changes smoothly. We have a lot of nice mathematics for that, since Newton, and lots of other analysis to go with that. But what happens if things are non-smooth, or we have these jumps? So for example, if we go back to our heat transfer problem, if we now add a thermostat, right, so that we have some target temperature where the thermostat wants to take us to, again, we have the same model that we had before, where the change in temperature just is proportional to the difference between our temperature and the ambient temperature. So as we see here above this blue line, again, we start heading towards the ambient temperature. But before we get there, we get below the target, the thermostat turns on. And instead of having just a single equation, we now have a separate equation where we add heat, and it starts raising the temperature. Okay. Now, what we sort of experience is not that we're jumping back and forth between these two, but that we actually hit the target temperature and ideally stay there, right? And so from a model point of view, that basically means, okay, somehow we're combining these two directions in a way to actually just hold us in one place. And also I should mention that we've actually added another feature as soon as we've added this switch. And that is that this ambient temperature, which was our equilibrium that we would just go and settle to before, that's now kind of a new mathematical thing called a virtual equilibrium. That's the equilibrium when we're above the target that we try to head towards, but we never really get there, right? But it's still telling us something about where our dynamics is actually heading, okay? But then with the heat, we actually, just stay at the target temperature. Okay, so what's actually going on at that target, right? Here, we've actually defined what's going on above the target and below the target. Do we actually have an equation that tells us we're actually going to stay there? And there are many ways you could actually define that. And that actually brings up, this sort of sometimes mathematical conundrum in terms of, okay, now we have multiple things happening sort of at this target temperature. What do we actually define? Now, a common way that we treat this is called Filipov, named after Filipov, who studied many, many versions of this type of problem. Simplest case is we take a convex combination of the two equations, essentially, put them together in the way that we actually just stick on this line. And as time goes on, we just stay there, okay? And that's actually what's called sliding. So already with putting in a non-smooth switch here that tells us we jump from one behavior to another, and that those two behaviors actually push us onto this target temperature, we have a new mathematical phenomenon where we just stick at that value. Okay, so that's called sliding. It shows up in a lot of different problems. We don't always have to do that, right, as we'll see. Okay, but then you could say, well, this is some sort of mathematical construction. Is it real? Is it correct? Is it the only way that we could write down this problem? Did we gain something? Did we lose something? You know, because we kind of just made up some new piece that told us what's going on in this line. You know, for example, you could say, well, what's really happening is, you know, we're actually going slightly below the target temperature, and then the thermostat's kicking us on, and then we're going slightly above, right? We're not really modeling that here. Does it matter? Right? So anyway, so those are just some questions to keep in mind as we look at a bunch of different models. Okay, and so I'll look at a few different models in different applications to kind of give us a little tour to know what different sorts of things that can happen. And you know, a lot of these ideas will come up along the way, and that is sometimes we can make things a lot simpler, at least to kind of understand phenomenologically, by using a simple switch, even though it might not be as mathematically nice and smooth, but it may make this problem simpler to think about, right? But then we may get new phenomena like this sliding along the way that we have to then think about. Is this correct? Is it, you know, is it the right mathematics? Is it the right physics? Is it whatever, okay? And then we can ask, you know, is that better than trying to, for example, in the thermostat problem, to model all the little switches that the thermostat may be doing to turn the heat off and on all along the way? Is it just simpler to say, you know, we just stick at that target temperature? Okay, and I'll also look at a few different areas. I'll look at a couple of what we call conceptual climate models. I'll look at models of human or balance in general, and then just a little bit on energy transfer, energy harvesting, all with some non-smooth elements. Okay, so the first example I'm going to look at is called, it's a climate example, modeling paleoclimate, basically very far in the past, glacial, interglacial periods. This is on the hundreds of thousands of years scale, so it's going back quite far. It's called PPO4 for a very simple reason. The two authors' named Palliard and Perrin start with P, and it was published in 2004. Okay, so basically the idea, so just to kind of walk you through, there's a lot going on in this model. We'll try to keep, I'll be very kind of simple in terms of my explanation. But the idea is here we have some kind of fluctuations in basically three main areas. At least this is what the PPO4 model basically says, is there's a lot going on, obviously, but if we look at three main target areas, that is the ice in Antarctica, the total sea ice volume, and the CO2 in the atmosphere, that we see these changes in that data from going from a glacial period to interglacial period. So by the data, I mean, basically you are taking ice cores or sediment cores, trying to look back in the history of the Earth to try to see, okay, when did we have different periods of warmer or colder climate? And so you have these sort of oscillations. Those are always coming up because the Earth has this thing called Milankovitch forcing, meaning there's slight tilt of the Earth, always kind of wobbling around, as well as in its orbit around the sun. It also has a bit of a wobble to it, okay? And so what is seen in the data, so you'll see some, like, let's say, more smooth curves here and some more jagged curves. The jagged curves are the data. The smoother ones are the model. But the idea is you have fluctuations in all three of these quantities, except you have a sharp drop in, you have a sharp increase in the CO2 that gives you the sort of start of these, where I put these dotted lines of the interglacial periods. Okay. And these are relatively short, but basically then cause a drop, for example, in the Antarctic ice and the total sea ice volume. Okay, more CO2, warmer Earth, ice melts. And so the model actually has, although it looks fairly smooth, the model results, these more wobbly curves, they actually have a switch in them, and there's going to be a trigger function that's going to be some sort of switch that goes on to start these interglacial periods. And so the model for this, I mean, there's obviously a lot going on, but if you just look at the model, again, each of the equations for the sea ice, the Antarctic ice, and the CO2 are just linear models, right? They're very much like our temperature model. They don't involve any complicated functions really at all. It's just kind of a difference between two quantities. That's it. That tells us about how things are changing. But the big difference here is there's a switch that essentially kicks on in a term in the CO2 equation, which suddenly causes a big growth in the CO2. And that growth basically is essentially over the glacial period as ice forms. The sea becomes more dense because essentially brine is kicked out of the ice, sinks, and actually can capture CO2 and store it deep. Okay, but over time, for example, if there's a lot of ice forming on Antarctica and in the sea, it gets harder and harder to store this CO2. And then there's some sort of fluctuation basically coming together with this Milankovitch forcing, where suddenly some of this CO2 gets released, and then basically you have this trigger. You get some CO2 released, warms, that continues, you release a lot of the CO2, and then you start the whole process again. So that's basically what's going on. And so this switch is basically just modeling the fact that this release of the CO2 on this long glacial scale is relatively quick. So it plays a role of it almost like a switch, okay? And it's capturing this sharp increase in the CO2. And the switch is essentially a Heaviside function, meaning it's zero all the time until once in a while f is this function here is going to be negative. And that involves the sea ice, the Antarctic ice, and this Milankovitch forcing, which is this I-60. That just means the fluctuation that we're seeing from this wobble of the Earth. Okay, and so just to see what that looks like, if I just track this, here again, V and A are just the sea ice volume and the Antarctic ice. Essentially, we have a switch. Okay, sorry, this pointer doesn't like this screen. So, so we have the switch, which is basically whether this F is positive or negative, that we can draw in the sea ice versus Antarctic ice plane. And the growth in both types of ice goes along. It hits this switch, and then suddenly we start increasing the CO2, and then we start melting the ice in the Antarctic ice. It comes around, and then we cross that switching surface again. So unlike the thermostat model, we don't stick on the switching surface. We actually just switch from basically the glacial period to the interglacial period, basically where we're building up ice to melting ice, and then we just keep going around and around like that. In addition, there are these extra wobbles that come along because of the Milankovitch forcing, and those can actually, help to cross the switching surface sooner or later, so there'll be some variation in that. But otherwise, the whole point is we get this, fairly complicated cycle, which is very simple linear type equations, but putting a switch in, and that really has a nonlinear effect that, gives us this chance to go back and forth. And as I mentioned, there's no sliding in this case, so we just keep switching back and forth across this surface. And then there's been some other work done on this to another phenomenon that we have in these non-smooth type systems is besides, crossing the switching, as we said, we have this wobble in the earth. So we actually have these extra kind of loops going on because of the Milankovitch forcing. So you can imagine some of these loops, they could cross the switching surface earlier or later, depending on how big those loops are. Right? And that actually gives us, variation in the lengths of these periods, basically on the length of Milankovitch forcing, which is about 40,000 years, right? And there's multiple frequencies actually in this. So this is just looking at this possibility of what we call grazing, that is where one of these loops just sort of touches or grazes the switching surface as kind of another type of route to crossing the switch, which has been studied in this paper. Okay, so that also introduces another type of transition that you would get called grazing in these non-smooth systems, where you suddenly get close to some kind of switch or some kind of dramatic transition. And then whether you cross that or not gives you a change in behavior. We'll see more of grazing a little bit later. Okay, so now we can just take a step back and say, okay, what did the non-smooth model actually allow us to do? I mean, in this particular case, first of all, we didn't have to model, a lot of detail in terms of, what's going on in the full, whole world during some switch between glacial, interglacial period. In fact, we kept it to 3 variables, very simple linear equations with just having this switching behavior. Okay, and so I think a nice quote from the PPO4 paper is to say, this is not a proof. I mean, even though it did a nice job of capturing the data, it's not a proof that this is really what's going on, but it does open the door to saying, okay, this is maybe some part of this cycle that we want to look more carefully at, get a better approximation to certain types of phenomenon. What do we know about this CO2 release? All of that kind of stuff. So basically to promote more in-depth studies and help us to focus on that, because we have actually very easy to interpret physics from these very simple models. Okay, to also identify some important scales, how fast this interglacial period is, and also different parameter regimes. So, it helps us in many ways to keep the model simple rather than, getting too complicated and getting caught up with very complicated functions. Okay, and just to look at another example of another conceptual climate model, maybe you have a sense what I mean by conceptual climate model. So again, it's not writing down all possible details of the climate, but rather trying to keep things on this conceptual level where we can kind of pull things apart. So this is another model, maybe of a phenomenon a little bit closer to home, the Atlantic meridional overturning circulation, or it's called the AMOC, right? And that's important because that's basically, it's called a box model because you're basically modeling 2 boxes. One is at the polar region, the Arctic pole, other at equator, and you're looking at how the circulation in the Atlantic is going back and forth, essentially pulling cold water down to the equator and pulling the warm water then back up north. Okay, and so basically the T1, S1 here are at the high latitudes, T2, S2, low latitudes, equators. This is from Potsdam Institute, which has a lot of nice kind of tutorials on things like this. This is the model from Dijkstra, another nice book has all sorts of conceptual models like this and talks about them. So here, instead of T1, T2, we have P and E for polar and equator. And the T here is temperature, the S is salinity. So this is basically a model of how we trade temperature and salinity in the water back and forth to create this flow and exchange, a circulation between polar and equatorial regions. Again, if you stare at this a bit, you see that the equations, the evolution, essentially just in terms of differences in salinities, differences in terms of temperature. Very, very simple, except now there's an extra term here, this psi, and we have the magnitude or the absolute value of psi here. And what is psi? Psi actually is just telling us the magnitude of an exchange, and it's based on differences in density. Okay. Now that absolute value is exactly what's going to be important for us today because that gives us non-smoothness. Okay, and so this is kind of a reduced version. You can simplify the model down to just the temperature and salinity variables. Those are actually differences. T is really the difference between temperature at the equator and polar, similarly with the salinity. And then everywhere you have this term that's basically the difference between this T and S. So that's like a difference of differences. But the whole point is we have these magnitudes or absolute values. That's actually a non-smooth function itself. So we have rates of change that are just, that may be non-smooth because of this absolute value. Okay, and then there are multiple parameters that come in here because of thermal and mass fluxes, but the one we're going to concentrate on is actually what's called the freshwater flux or freshwater forcing. And again, you can think of that as melting ice, right? That gives us changes in how much fresh water we have. Okay, so unlike the PPO4 model, here we actually have a steady state. That is, we don't go into some circulation, at least if we just fix our parameters. We either go to one state or the other, okay? And so this is just saying, we can write this in terms of T minus S. So this is saying, I could either go to an equilibrium state, which is larger values of T minus S for my freshwater forcing at a particular value. If my freshwater forcing is higher, it goes to a lower value. And so the upper value is called the temperature dominated region. The lower value is called salinity dominated. Now, right now, we're in temperature dominated AMOC, okay, which means we have circulation from north to south and back and forth. That's maybe good for us up here because we're actually warmer in that scenario. The AMOC has tipped in the past, and in those scenarios, we don't get this exchange, which means the northern hemisphere stays colder and doesn't warm up so much, and the southern hemisphere is hotter. But it obviously is flipped back and forth. Okay, so you know, how does that flipping actually happen? Well, our freshwater forcing does not have to stay fixed. So this is basically a model with hysteresis, meaning if somehow our freshwater forcing could increase, that is, more ice is melting, that means we can follow the temperature dominated state for a while, but eventually if this A to 2, the freshwater gets too high, there's no place else for us to go except down to salinity dominated. But then, okay, if somehow it could decrease again, same thing would happen. We'd follow that salinity dominated until there's no place else to go except back up to the temperature dominated. So this is just our typical hysteresis loop. If we have some parameter which is increasing and decreasing, where we have a range where we have two possible equilibrium states called bistability. Okay? So very common for, especially in models of, for example, ecology. So here's just another example where we have two states, high vegetation density, low vegetation density. We have a grazing, right? So if grazing increases, we start reducing our vegetation until we can no longer stay on the high level, jump down to the low level. The grazers go away and the vegetation recovers. But it doesn't immediately jump up to the high level, right? It follows this low level for a while, then eventually no place else to go but to go to the high level. And I put the budworm example here as well, because that's one that shows up a lot in the Canadian North. And you can see here where, for example, the budworms can be in some refuge level for a long time. And then if the resources are strong enough, there can be a large outbreak. Okay, so again, this typical transition, so this is often called tipping, where we fall off of these equilibrium states as we vary certain parameters. So when they say the AMOC is tipped, that's what we mean. These are called fold bifurcations, hopefully for an obvious reason. The curve sort of folds around. It folds from something stable to something unstable so that we have to jump to another stable state. And then the bistability, having a region of parameter space where we have both is common. Okay, so so now we can go back to the to our AMOC example. Now the big difference maybe between what I just showed you, in this particular model, this is more of an S-shaped curve, meaning the curves are actually smooth. Okay, so back to the smooth, non-smooth. But in the AMOC example, this change right here from salinity back to this other curve is actually non-smooth, whereas this one, of course, obviously a parabola is smooth. Okay, and so you could ask, does it matter, right? In our hysteresis loop, if we're dropping off of one state, going in either direction, either from low to high or high to low, does it matter what the shape of this fold bifurcation is? Okay, and it's and I should say again, you know, this is coming directly from, remember we had this absolute value, which was our non-smooth part of the equation. Okay, so I'll just give you a few examples where we see differences, so you can get a sense of what's different. Okay, so again, we're going to look at this model from the point of view of where the freshwater forcing, this A/2, is not fixed. So it could be varying, right? We could be increasing it over time, decreasing it over time. We can also have fluctuations. So we'll say something about that. So for example, if we're just slowly changing our freshwater forcing, so we capture the slowness with some small coefficient epsilon, then we could ask, how do we actually, follow this branch? Do we drop off faster? Do we drop off? Is there a lag in the drop off? Now there's a lag when you follow this slowly, basically, because it doesn't really quite settle down to equilibrium. It gets sort of close. But it still kind of remembers that the equilibrium is there. So you can get beyond this tipping point when things were just constant and actually drop a little bit later. How much later? Well, in the smooth case, it goes like 2/3 of this coefficient epsilon. In the non-smooth case, it looks like epsilon log epsilon, meaning just somewhat larger than epsilon. So in this case, we see a much smaller lag in the non-smooth case than we would in the smooth case. Probably more important is what happens when we have fluctuations. So again, we're thinking of A/2 with some kind of something that's fluctuating over time. So you can think in terms of annual fluctuations, right? More or less ice melting. There's also, decadal circulations that are global that also feed into AMOC. So that could be over, decades or even centuries where you have these fluctuations. So it could be high frequency, low frequency, all different options. And this is just showing what happens. So if the black line is just if we don't have any fluctuations, just sort of the slow, little bit of a lag. But the pink lines are when we add in some sort of regular fluctuation in the freshwater forcing. And again, you could ask, this actually generally advances the tipping, so you'll have tipping faster. How much? In the smooth case, it advances by the ratio of amplitude to frequency squared. In the non-smooth case, it just goes by amplitude to frequency. So depending on whether you're high frequency, low frequency, these could be quite different. Okay, there's also a lot of variability, particularly in the low frequency, in that there's much more of a history dependence, or if you like, phase dependence, or what were your initial conditions. And this is just to show here negative values are lags, positive values are advances. And with just a very slight change in frequency, you can go from a large lag to a large advance. And that's again because we have this very sensitive history dependence in those sort of problems. That happens in both cases. And then we can also ask about noise. There's been many results given on smooth fold over time that says you will have noise-driven tipping if the noise goes like the square root of this slow rate of change. Whereas in the non-smooth case, you have noise only has to be bigger than the rate of change itself, not the square root. So in fact, much smaller noise will cause tipping in the non-smooth case than in the smooth case. Okay, so we can see all these differences. And so that kind of comes back and says, do we actually know which is which? And I forgot one more. Actually, the whole mathematical structure of this non-smooth fold, it brings up a whole different type of mathematical structure that we don't see in the smooth fold. And essentially that can be captured by thinking, okay, if we start somewhere near the salinity dominated branch and then settle to it, we actually do that in some oscillatory way, saying basically this is a focus. But of course, on the upper branch, this is just, we're just going to move away from, for example, this unstable part as soon as we're a little bit off of it, okay? You cannot get these two types of behavior coming together in the smooth case. It will not happen, okay? So it's really, we can have this basically because we have some kind of switch here from the absolute value that lets us kind of piece together different types of behavior that you won't get from just a smooth function. And what that actually allows is a potential for a resonance phenomenon with some sort of forcing here, so that these oscillations can actually drive you into tipping. So you have other mechanisms for tipping that you wouldn't have in the smooth case. Okay, and so essentially, again, this is a conceptual model, so I'm not trying to say like everything's smooth and we're going to tip faster or slower or anything, but it does raise the question of, which is correct? Do we need to have a better resolution of what sort of tipping or fold that we actually have? How do we get that? What sorts of conditions do we need to think about? And also, again, all these influences of different outside noise and fluctuations and so on. So it does point to hypotheses that we do need to test. Okay, so with that, I'm going to change directions radically, except for the non-smooth part. It'll still be non-smooth, but we're going to talk about balance. So radically, I mean, we've been talking about kind of geological scales, and now I'm going to talk about essentially neurons and how that actually plays a role in models of balance. Okay, and so I have a couple of pictures here on your left. I guess we have just a little sketch of, basically a typical observation you might do to look at if someone, to monitor someone's ability to balance, right? Where you essentially, there's a camera here, it just points to essentially the top of the person's head. And if they were standing perfectly still, not moving, you should see on this graph, this is the angle from vertical, you should be at 0, right? And if you're not changing the angle, that should also be at 0. So you should just be right in the center. Now, what really happens, this is not falling over. This is just normal standing there. You tend to move around a little bit, and you're kind of moving in and out of the angle. but always coming back and not falling over, okay? Similarly, if you did the experiment of balancing a stick on your finger, right? If you measured the top of the stick, you would see something like that as well. And so over time, basically, you're seeing this variation of angle and the change in the angle, but in such a way that we don't fall over. Okay, so you could ask, what's the model for this? Well, actually, we just heard a little bit about inverted pendulum in the tutorial. So the simplest model is to think of this as an inverted pendulum, right? Instead of having a pendulum that swings down, we're having the pendulum stand up. Now, if we didn't try to control it and just tip the pendulum, of course, it would swing down and not want to stay upright. So there has to be some sort of control. Now, we could put the pendulum on a cart and move the cart back and forth. That would kind of adapt to try to essentially balance the stick. I put this down just because I thought it was cool that Wikipedia actually derives the equation for this for you. But we have an even simpler model, which is just the simple model of, this is just the model for an inverted pendulum. So this is just thinking of the pendulum, but with a control, a torque control that basically keeps the pendulum upright. And that's often used as at least a toy model. If you think in terms of your ankle as the torque control, your ankle is very important in balance. Okay, and well known is this, how do you stabilize an inverted pendulum? Well, one way is with some vertical oscillations, and it doesn't stabilize it exactly at 0, but it does oscillate around, but not flying off. This is without control. It would just fly off, or at least the angle would increase. Now, the human version of this is lots of really nice results by John Milton in human experiments in stick balancing, is putting the human on a vibrating platform. Does that actually help to stabilize the stick? It turns out that you can actually extend the time until the stick drops in that case. Now, it isn't just because of the vibration. There's a lot more going on there, but that was kind of a funny analogy. Okay, but back to our simple case where we just have the inverted pendulum with some sort of control. So a typical control, very simple control you might consider, is called PD control. The P is for position, in this case, the angle, right? So we have one term that's just theta, the angle, and a second term that's the derivative of theta, the rate of change of theta. And so we have another term proportional to derivative, so position and derivative PD control. Okay, great. Now, the other complication in this, from the biological considerations, there's a delay. Jacques will like this, I know. So the delay is essentially because you don't immediately adapt to falling over. It takes a while to fix that, right? And so there's going to be some delayed feedback in this control. So it's not just dependent on the angle and its derivative, but at some time in history. Now, on top of that, biologically, the control is not on all the time. And here's where we have our non-smoothness. Okay, so in fact, it's actually can be useful not to put the control on all the time. And we'll see that in a minute. Also say a little bit about noise. Okay, so what does it mean for the control not to be on all the time? Well, in the phase plane, so basically angle versus derivative, we have it on no matter what the state is. But here we have where the control is off in certain regions. And if we stare at this region for a bit, we can realize, okay, in this region, the angle is negative, like let's say to the left, but the theta change in theta is positive, meaning we're pushing towards the right. So we're actually correcting, even though we're a little bit out of vertical. So why bother? We're going in the right direction. Let's not control. Whereas down here, if theta is negative and we're moving even more negative, yeah, then we need to turn on the control to make sure that we don't fall over. Okay, so there'll be regions where we just don't correct because, okay, we're already correcting in the right direction. Okay, so what does that actually mean for the inverted pendulum? Does that actually stabilize? And how does it do that? Well, essentially, if we're in one of these regions where we're about to fall over, the control kicks on and basically pushes, in this case, the change in the angle down until it becomes negative. So we start pushing back the other way. There's a bit of delay, so it doesn't immediately turn off, right? So it stays there for a bit, then it turns off. Okay, then you start to fall again, and it turns on, kicks back. So, unlike the thermostat, we don't just stick between on and off. With the delay, we actually oscillate back and forth. And in fact, if the delay is too long, we actually go around and around. But still, eventually, we'll get somewhere to the middle with this. And the good news about that is, as I didn't really mention here, if the control is always on, we have a tend to overcorrect. So we tend to oscillate back and forth if the control is always on, especially with this delay. But in this case, with the off, we tend to move in. Okay, so you could ask, do we always have to go in? And another way to say that is, as we're zigzagging back and forth, can we actually close these orbits? And you can go ahead and do that calculation and see that. In fact, you can get closed orbits that just kind of move back and forth across this basically finite angle, okay? And even do the stability and see that a vertical where you have zero angle, it can be stable for a large enough control. But up here we have a branch of blue, a blue branch here, which says we can have some other state that's also stable that just corresponds to zigzagging at an angle. Okay. And so actually we can move between those two. They happen to be bistable. That is, for smaller values of the control, we could have either one. And in fact, some of this has been observed where if you give someone like the wrong visual field that tells them, okay, the world is tilted this way, they'll actually, they don't have the right correction, not strong enough control, it'll actually sort of lean. So there can be stable states like that and actually observed in certain tests. Okay, and just to say, in this case where we can actually be in either one of these states, standing straight up or zigzagging a little bit to the left or right, noise can actually kick us back and forth between these states, as is typical of bistability. So noise also becomes important. Okay, so this kind of gives you a sense of, this switching behavior and combined with delays and all these other biological considerations of all sorts of other types of phenomenon that can actually occur with this switching. And there's many, many models like this in the health sciences. Neural examples, ecological examples of viability, activation in terms of, let's say, antibiotics or other types of activation, gene regulatory systems, and so on. But again, a lot of the modeling in terms of thinking in terms of simple models where we take care of complicated nonlinearities just with switches or other types of fast transitions can actually be really nice in terms of interpreting what's going on physically, rather than trying to get kind of bogged down with complicated nonlinear functions that might give you kind of similar behavior. Okay, so I'm just going to spend the last couple of minutes on a couple of just very quick topics. So as I mentioned with the thermostat model, we had this thing called Filipov, which essentially said we combine the decrease and the increase in the temperature through dynamics in a way that we just stick at our target temperature. And so there's been a lot of work by Mike Jeffrey on what happens if we define what's going on in these switches in different ways, because generally we have multiple ways to define the dynamics there. This is just an example of, this is the oscillator, a little bit more complicated than a pendulum, but looking at essentially two state variables, where in a simple Filipov type definition of sticking, essentially a forcing with two different frequencies or forcing in two different regions. Sticking them together in a Filipov way, we get this kind of funny shaped orbit, but it's an orbit. Okay. Whereas if we combine this combination of forcing with different frequencies in a different way, where we look at combinations of the frequencies, then we get a much more chaotic type of behavior. And then beyond that, you can ask, what if I actually don't resolve my computation enough to really capture what's going on inside the switch? Then you get something else, that is, you kind of go back to the Filipov. And so there's many examples like this, or where you can add noise, and does it change the behavior of what's going on in the switch, or do you exit the switch? Many questions like this in terms of how do we actually define these things? Does it actually give us the correct behavior? So still a lot of open questions there. And then I've mostly been talking about switches in these examples, but I just want to spend a little bit of time on vibro or impact systems, in this case, vibro impact systems. I'll talk more about this on Wednesday, but I'll just give you a little bit of the flavor of that now. So the simplest example of impacting system, at least I think, is the bouncing ball, right? You drop a ball, it bounces on the floor. Basically, if you model that as just hit the floor and come back, you have just a non-smooth switch, basically, or non-smooth condition that takes you from moving in one direction, the ball going down, and coming back up. Now, in that case, it's not just a switch. You actually have to use essentially Newton's laws of motion in order to transfer velocity and so on. But basically, you basically change your velocity at impact. You don't cross a switch and then just change in the direction of motion. Okay, and you can get this is an example of the bouncing ball on a vibrating floor, right? So you keep the ball bouncing, and you can get all sorts of different types of regular behavior, chaotic behavior, all sorts of. And now you can extend that simple idea to other areas of energy. So one area is thinking of how can we use impacts to actually damp energy. And another one is how do we actually use impacts to capture energy. And then, yeah, well, I guess I want to talk about friction. But here's just a very simple example of how do we use, oh, this is actually not using impacts, but a typical way we might damp energy in a system. This is a very common term, tuned mass damper. So essentially your shock absorber is a tuned mass damper. That is, it's tuned in a way to actually reduce the vibrations in your car when you hit a pothole. This is the example. I really like this because this is the Taipei 101 skyscraper. And the visitor center doesn't say visitor center, it says tuned mass damper, right? So that's exactly what you're going to look at. And it's a giant pendulum, okay? And so essentially the basic idea is as you're experiencing, let's say, an earthquake or some other motion, the pendulum should swing in the opposite direction and reduce the sway of the building. And it needs to be tuned so that you damp the right type of vibrations. Okay, and so now that's not the only way you can have a tuned mass damper in a building. You can also put these kind of sliding, rolling things in the floor that are masses that actually move in opposite directions as well. And again, sort of damp those oscillations. But a new version of that is actually where you let these sliding things actually impact the end of the cavity in the floor, right? And so you exchange energy by impacting, but also through the fact that an impact doesn't have a single frequency. An impact is actually represented by multiple frequencies, so you can actually transfer energy in an intermodal way, or meaning across frequencies. And this is just a recent study using exactly these sorts of systems in a scaled version of a couple of different, the inputs from a couple of different earthquakes. The energy going in the system from the tuned mass damper is up here at the gray level. Whereas with this, what's called clearance contact, meaning you actually impact the damper impacts the side, you actually transfer more of the energy across modes and damping zones. So that's kind of a new interesting way of, okay, how can we use impacts in a very simple way to get a much more complex and beneficial damping. The other nice thing is you don't have to tune anything here, right? In fact, you don't want to, because you want to capture a range of frequencies. Okay, and then as I mentioned, there's energy harvesting. I'll talk more about this on Wednesday, but just to give you the schematic, basically you have a capsule. It's shaking. So for example, it may be attached to a building or a bridge or something. It's the idea is to power a sensor. Or there's even some toy versions of this where you put it on your backpack while you're walking. But anyway, the tube is moving back and forth. There's a ball inside. It's also moving back and forth. It's hitting either end of the capsule. The capsule has a dielectric polymer on it so that when the ball hits, it stretches the polymer, and with the electrical properties, you have a change in capacitance and you can harvest energy. Okay, and these are some of the experiments that we've been doing with my collaborators in the UK. Basically, the idea is you have lots of different behaviors that can happen in terms of hitting either side of this capsule. How many times do you hit, in what order, and so on, right? So this is just a graph of different types of impact velocities you can get. But the problem is you have lots and lots of different states. And while you can construct each one, in some sense, you want to know much more about global properties, like what's going to happen, what's the most likely state that you're going to end up in. And so I'll talk more a little bit about that on Wednesday. So just to give you a little preview of that. Okay, and so as I mentioned, my answer to this question is the world smooth or non-smooth? Hopefully I've given you a sense that the answer is yes. But as we can see, the non-smoothness introduces a lot of new mathematical questions and hopefully motivating new mathematics as well, as maybe we move out of some of the maybe nice theorems we have for smooth cases and start thinking about, well, what if we don't have that anymore? And then as I was writing this, I was thinking how many things in sort of the artificial intelligence, machine learning world are actually non-smooth. So for example, in neural nets, you often use these ReLU activation functions to essentially tell you how you transfer information from one layer to the next, which neurons are actually activated, meaning are they actually on this part of the activation function, or are they zeroed out on the flat part of the activation function? And so that's naturally a non-smooth function that shows up. And also, if we think about L1 optimization, we think in terms of thresholds, sparse representations or sparse solutions used in compression and other systems where we want sparsity. Again, these thresholds are kind of like switches. And in fact, we have some results showing that you get something like a noise-driven chatter, something like this balance model that kind of flipped back and forth across the on-off switch that actually kind of kills your convergence. So when you're trying to come up with some sort of optimization or solution to some sort of, let's say, imaging or parameter fitting model, these thresholds can sometimes be tricky. So understanding non-smooth properties there is also very helpful. But many, many examples like that in the let's say, maybe not physical world, but the machine learning world. Okay. With that, thank you very much.
Do we have any questions? I have a microphone here, so.
Okay. So if you have a non-smooth force law, how do you define the force in terms of geometry in these cases?
Sorry,
How do you define the forces in terms of gradients of some potential?
Yeah, so you can write down potentials for these things. Yeah, you can definitely do that. I think the problem is, like we have a lot of, maybe ways to then analyze the problem that might depend on like having, that the potential or something is smooth rather than non-smooth. So you might not be able to use all of those methods, right? I mean, so good example of this are like ratchets, right? Which are basically a non-smooth, force where you sort of jump over a wall and then suddenly it's non-smooth, right? So there are some methods that actually go through, but then sometimes you actually have to develop some type of new approach. So for example, these energy harvesting, we do a lot with maps rather than, derivatives and things like that. But
Okay.
yeah, that's what motivates the new math. Yeah, for
Okay.
sure.
Okay, thank you.
So you gave the example of the switch, right?
Mhm.
Where because of the non-smoothness, you saw things happening faster. Are there examples where it goes the other way, where putting something non-smooth in is going to slow down the switching?
Yeah, for the hysteresis problem
Yeah.
you're talking about, right? Yeah, that's in the particular sense of hysteresis. Okay, so there we essentially took, sort of the canonical, although there's not really canonical non-smooth version, right? But you could have other types of switches. Well, I guess this comes to this definition of how do you define what's going on at the switch. So you can actually have, some sort of dynamics within getting stuck on that surface that could slow you down. For example, in the energy harvesting problem, you can have dry friction where the bowl can actually get stuck to the side of the capsule, so it's not always moving, right? And that actually slows things down. You get less energy, but sometimes it can be nice because it actually gives you more regular behavior rather than going into certain types of chaotic behaviors. So that's where you actually combine the impacting with switches. Essentially, there's two types of non-smoothness there that do give you an advantage sometimes.
Other questions? If not, I think there's wine and cheese. And let's thank Rachel.
Okay, thanks.